conformations here for the gauge part. So let's start off with that. So what is going to be happening when you are going to be having a conformation which is called as gauge? So let's start off with the basic one itself. We'll take with hydrogen and OH. So this is the one you guys would have discussed in school, I suppose, right? Ethylene glycol.
Yeah, ethylene glycol here.
So ethylene glycol here, you're going to be having the gauge conformation being the most stable one. So your question here is, why is it that the gauge is more stable? Why not the eclipsed? Why not the other ones? Why is it that it is not going to be that? Right? So now, whenever you're going to be having a question of this sort, what is going to be the issue here?
The hydrogen bond.
Good.
Like,
So what have I taught you so far? Till now, when you're having something like this, a question, this is a deep question, right? When you're having a deep question as a problem, what should be the problem? Where will be the problem?
assumption.
Good. What is the assumption you have to start now questioning? You basically told me already.
Yeah, when it's eclipsed, it should have hydrogen
Not
bond.
that hydrogen bond.
Oh, hydrogen bonding, yeah.
That is what you need to start understanding a little bit more carefully, because there is a hidden assumption here, which is mostly going to be solving my problem here. Right?
Yeah.
Because everything here has to do with hydrogen bonding.
Correct. Yeah.
Right? Everything here has to do with understanding hydrogen bonding. And there has to be some assumption here, which is putting a curtain in front of my eyes here. Which is why I'm not able to clearly understand what is happening here. Because the only concept here is hydrogen bonding, and something behind it is sticky. So let's go for hydrogen bonding assumptions. What is hydrogen bonding? What is happening in it?
Weak bond between a hydrogen and an electronegative atom.
Repeat.
Bond formed between a hydrogen and an electronegative atom.
I did not want that answer. That's why I told you to repeat.
Oh.
When I'm asking you to repeat something which is obviously seeming correct to you, it's not that you're wrong. I just don't like that answer. I want you to rephrase the same thing slightly more carefully. I remember I discussed a little bit on hydrogen bonding with you.
Yes, sir.
So why is it that the hydrogen specifically attached to the electronegative atom is the one which is showing? What were the two things I would have discussed on hydrogen? I remember I would have normally, however much your teacher does in your school, I would have discussed these two things. I would have talked about ammonia, water, and HF. Yes or no? Comparison of boiling points. Did we discuss that or not? I mean, from the point of view of which one has higher boiling point and why.
Yes, sir. We did that. Yeah.
So
Yes,
what was the reasoning there? What was the logic there? Which one has the highest boiling point among the three?
Sir, NH3 has more hydrogen bonds, so NH will have more. No, you said something else. Wait, what are the compounds again?
The logic you remember is correct.
But you gave priority for that.
But you basically stopped thinking beyond that. How do you decide what decides the number of hydrogen bonds? Which guy has maximum number of hydrogen bonds? Water, NH3 or HF?
NH3. No, sorry, H2.
Why?
Because it has two alone.
What is the necessity for a hydrogen bond?
Hydrogen.
What is a hydrogen bond? What do I
between
mean?
lone pair of
You're
Lone pair
starting
of electronegative atom and then hydrogen.
which needs to be clicked now. So what is a hydrogen bond? Come back to what is the assumption I'm asking you to question now. What is a hydrogen bond? Be as specific as you can.
The bond between a hydrogen and the lone pair of
Interaction between what? Do not call it a
hydrogen,
bond. Interaction between
hydrogen and lone pair of electronegative
hydrogen. Be more specific. What type of hydrogen?
atom. Bonded hydrogen.
What type of hydrogen? Hydrogen with a very high delta plus.
Oh, yeah, correct, yeah.
Right?
Yes.
That is the bare minimum requirement here, correct?
Yes.
Interaction between a hydrogen with a very high delta plus and what else?
Lone pair of electronegative atom.
Again, be more specific. Lone pair of what?
Delta minus. Atom with delta minus. High delta minus.
Be more specific. In the discussion which we had talked about in hydrogen bonding, I will discuss only two sets of examples. I will discuss the H2O, HF, and NH3.
NH3.
To signify and make your assumptions crystal there as to what is a hydrogen bond. Then I would have discussed about how you're going to be looking at only second period elements with delta minus. Right? I would have discussed something related to that. I would have talked about carbon being capable of showing. I would have probably touched upon chloroform.
You told carbon. Chloro is something you told.
Right? So I would have discussed about why carbon is going to be the significant other which is possible, along with nitrogen, oxygen, and fluorine. Why not? Why not chlorine? Why not something else?
Yeah.
What was the reason?
Size.
Good. So effectively, the idea there is it has to be a second period element. So the lone pair has to be in the goddamn vicinity.
Okay, understood. So it should be lone pair
between the lone pair and the hydrogen delta plus is critical there. That is the other significant thing which you need to start understanding. So effectively, let's go back. Lone pair of second period delta minus species. All right. Now, let us now look at the other thing which I was very strict about. When you said bond, I got pissed off. I asked you to basically call it as an interaction. Yeah. Why?
It's not a complete bond.
What do you see? The problem which I had was not with that, with anything else. I had a problem with bond. What does a bond mean? When you're going after core assumptions, you should never define random things and make assumptions there. Extra assumptions there, extra definitions or extra assumptions there. We have enough assumptions here already to play with. What are the assumptions we still have left? We still have what is mass, what is charge, how do they interact? All of those basic assumptions are still left over.
Yeah.
We are not through the assumptions yet. So now let's not add extra assumptions of bond over here. So a bond effectively is something which is a strong interaction. Strong attractive interaction. As simple as that. Correct. At the end of the day, it's an attractive interaction between the two species. So in this particular case here, a hydrogen bond is going to be an interaction which is not as strong as a bond in all cases. It is something which may become reasonably stronger. And this interaction is going to be something where it is a KQ1, Q2 by R squared type of interaction only. Like every other interaction. It's a covalent bond, it's an ionic bond, it is a H bond, I don't give a shit.
All governed by the same thing.
Resonance, whatever the fuck you want to look at, all are interactions between electrons. Which means all are governed by KQ and Q2 by R squared or KQ and Q2 by R. Governed. I hope you are seeing the other hints which are coming over here. I'm not going to be stressing upon them beyond a point. So all are governed by the same system of equations. Now, how you understand this, that is different. How you interpret it is different. Now, coming back to this particular part here. So when I said it is an interaction here, why is it that this is not comparable? If I'm going to be linking up these stuff which you are already supposed to be familiar with, ionic bond, covalent bond, and all of those, let's try to link them up and try to see all these together now. So if I'm considering an ionic bond, in that there is going to be Q1 and Q2 having full-blown charges. Where it can be a plus some electron worth of charge or plus some X into electron worth of charge, Q1. Like say sodium plus, now it will be 1 positive charge. If it is calcium 2 plus, it will be 2 positive charges.
2 and 2 evens.
So Q2 also is going to be something which can be a negative electron charge, or it can be some Y into negative electron worth of charge as well. So this is also going to be multiple possibility. This is for ionic bond. And the distance is also going to be tremendously lesser in the ionic bond case. The R value is going to be lesser because the ions are more strongly attracted. So they'll be closer together as well.
Yeah.
So in the ionic interaction, this is smaller. The Q1 and Q2 are larger. Correct?
Overall forces.
Let's talk about other types of bonds now. So that is going to be the best type of interaction. That will be the strongest. The next one which is going to be at play is of course going to be polar covalent. Correct?
Yeah.
In a polar covalent, the fellows are already bonded by a bond. So they're already chained together.
Yes.
Yes, they are chained at a distance, certainly. But they are chained already.
Yes.
And they are having delta plus delta minus. So the charges are not that heavy, certainly. Not by a stretch. Not by a huge stretch. And you have learned that in a bond like H and F, where the electronegativity difference is how much?
Like approximately 2 point.
Good. So you remember from chemical bonding that there are only like 3 or 4 pieces of data your teacher would have given you an electronegativity as well.
Yeah.
Which one did he give you?
Fluorine is 4.0 and then hydrogen is 1.9, I guess.
2.1, but go on.
Oh, and then this, what's this one? No, nitrogen is 3.7 something. The oxygen is 3.7, I think.
3.6, 3.5, 3.6. Nitrogen and fluorine are approximately 3. And they will be having carbon at approximately 2.5.
2.6.
And 2.55, 2.54 kPa. And you'll be having, other fellows, other halogens below 3. 2.8. That's the goal. That's all you need to know in the electronegativity values. So now, why those?
What? Can you repeat?
Why those?
Oh. Because
what values are to be learned so that you connect the pieces here. And in organic, wherever necessary. The carbon and hydrogen values are given to you for the organic bits there. Carbon and hydrogen bond, if you're looking at a CH bond, what is happening? The value which was given to you, which is going to be 2.55 something. That is going to be for an sp3 hybridized carbon.
Yeah.
All right. So when you're going to be going from sp3 to sp2 to sp, you're having increasing percentages character.
Yes.
Which means increasing electronegativity.
Yes.
We had already discussed that bit a little bit while back when one question I had, I would say, I think atomic structure case upset. I think we had discussed penetrating power associated with that.
Yeah. Yes.
So, all right. So now, that is going to be the piece which will connect over here. So if you're going to be having, say, a carbon which is going to be sp hybridized, you can think of it as close to 2.6 and a half, 2.65, 2.7 kPa. Electronegativity wise.
Yeah.
Now, however it is, HF bond barely has like 30 to 35% ionic character. HF. Right? And in HF, you're having, what to say, an electronegativity difference of 2 to 4. So when you're going to be considering polar covalent bonds, that is going to be the most polar covalent bond available. and that is going to be having the maximum polar covalent attraction possible. And even in that case, the polar covalency is approximately going to be like only 30 to 35%. So polar covalency is nothing compared to ionic. Ionically, the R is going to be so much more smaller, and you're going to be having the plus and the minus. The quantum of charge is going to be so much more higher. So that is basically the difference between R and the polar covalent. Now consider your hydrogen bonding. This is like some tiny crappy bit which is like nothing. Unless and then there are circumstances which decrease the R value here significantly. You're never going to be having the hydrogen bonding being as effective as anywhere near even a weak covalent bond. So if you want the hydrogen bonding to be more effective, you need to have the hydrogen bond happening between a hydrogen which has a high enough delta plus first. Some other species which has enough electron density also. Happy enough to give. Delta minus should be high enough that it can happily give away. And furthermore, distance has to be brought in as much as possible in an artificial manner, at least as close as possible. That is the basic requirement. Now, are these features clear so far?
Yes, sir.
Now let's go for the real KQ. Let's go for the real actual thing there. So when you're going to be having the structure, so let's draw the structure. The reason why it is a little bit more confusing to understand is because you can't imagine the spatial orientation properly. So let's go for Newman projection. I'm assuming you have been taught Newman projection by now already, yes?
Yes, sir. Yeah, that's what I know.
You know how to represent this in Newman projection, yes?
Yes.
Do you know what representing in Newman projection means?
Yeah.
So let's take a simple carbon-carbon system. So let's take this as your, what to say, ethylene, or that's ethane, okay? So ethane, if I'm going to be looking at the conformations possible, Newman projection is going to be something where we have a front carbon and a back carbon. So effectively, this is the same thing. You're going to look at it from literally the point of view which you're looking at it through now in the camera. So you're going to be having a front carbon and a back carbon point of view. This carbon is going to be the front carbon. This carbon is going to be the back carbon from your perspective. So the front carbon is going to be represented as a dot, whereas the back carbon, which you cannot see, is going to be represented as a circle. All right. So front guy is the dot and the back guy is going to be the circle. The front guy's bonds are literally going to come from the dot. The back guy's bonds will come from the circle. Fair enough?
Yes.
So let's start with that. So we're going to be having front and the back. Now, I'm assuming you have already got familiar with Y inverted Y. All of those are fairly clear.
Yes,
Eclipsed and staggered are perfectly clear now so far, yes?
Yes.
Okay. So when you're going to be having staggered is going to be a Y and an inverted Y in such a way that the bulky fellows are completely opposite to each other. Such that steric strain is minimized as much as possible. So are you clear with what is meant by steric strain so far?
Yeah, somewhat.
Steric strain basically means fat groups which are present. Think of it like any system which is going to be electron rich is going to be requiring some space to put those electron densities. Because electrons inherently hate each other. All right. So electrons hate each other. So when you want to pack a set of electrons in a space, you need to make sure you're providing sufficient space to pack those electrons in.
Okay.
If you're not giving enough space, you are basically creating a region where there is going to be some instability there. Some repulsions are there, which is chaotic. Okay. Now, let's get to this part here. So I'm assuming your understanding about staggered is clear. That means you understand also what is meant by gouge. What is meant by gouge then?
The bulky groups are next to each other. Next to
Bit
meaning
more
like
clearly, please. What is meant by gouge?
the bulky groups are at the
No, 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 no.
oh
Let's start with what is gouge first from the real perspective. Gouge is a form of staggered,
oh yeah
but not completely.
yes
Fair enough?
Hmm.
So think of it as it is a form of staggered conformation, but it is not a completely staggered conformation. It is anything in between, technically speaking. All
yeah
right. Anything
yes
in between, you call it as gouge. That's the truth. Okay. Now let's start understanding what this means here. So in this particular case here, what is happening is this is one carbon, this is another carbon. We are having hydrogen and hydrogen here, and we are having hydrogen and hydrogen here. They are telling us if I'm having a fluorine here and an OH here, or let me write it a bit more clearly. If I have an oxygen here and a hydrogen here, they are basically telling you that this interaction is better. Correct?
yeah
Compared to if I'm going to be having something like this.
uh, yeah that's it.
I mean, your issue is something on these lines, correct?
Yeah that's it yeah
This looks closer.
yes but is it maybe because of the bulkiness
So
the person
this is where the assumptions behind the question need to be challenged. Why did I ask you to go through the entire bit of hydrogen bonding? What was the entire purpose of that storytelling there? Can you now guess what was the point I was really interested in driving home completely? I told you a story, right? I
yeah
took you across a story. Summarize and tell me which point was a superhero point with respect to the continuation of our story now. Do you understand what I'm asking?
yes sir.
Uh, so what did we do? I sat and summarized hydrogen bonding for you,
Hmm.
right?
Yes
Special emphasis on some points, the overall assumptions. Now, in today's lesson, which guy is the champion? Which point is the one which we are looking for closely?
interaction
You got the direction where you need to go correct over here. Now go deeper. Which point in the interaction was I really interested in stressing on?
the lone pair of second period
True, but more specifically, please.
oh it should be small oh but no, no, nothing
I'm interested in the space.
space
That is, the R value has to be as low as possible because we are never going to have the Q1 and Q2 ever being sufficient enough here, right?
correct yeah
That is never going to be happening ever. But the only way to basically look at it is the R value has to be smaller. But now the next question becomes, what is that R? What is that R? The R is this.
distance between these two yeah
So now we need to start seeing where are these two guys. So is it the fluorine which I should be really looking at drawing over there, or what should I be looking at drawing there? I should draw a lone pair of fluorine and then check
yeah
truly what is the distance there.
correct yeah
You understand the point now?
yes
So let's put that and see. So if I'm going to be considering an OH, I can imagine an OH group like this. An oxygen is going to be technically tetrahedral as well, correct?
yeah yes
Right. So that oxygen fellow is tetrahedral, but the guy has got two lone pairs. Correct?
Yeah.
So I'm going to take this as an oxygen. Another tetrahedral fellow. Okay. I'm going to connect that guy to one of these locations. Fair enough. So this was my original carbon and carbon. But this fellow, which is going to be having the blue fellows are lone pairs. So this is not a carbon, this is an oxygen now actually.
Yeah.
And this
That's
guy
a hydrogen. Yeah.
You understand the point now?
So, but we need to focus on the
Calm down. We are not done.
Okay.
We are not done. This guy represents a fluorine. The red fellow. All right.
Yeah.
And this blue guy represents an oxygen. All right. So let's start. So the blue guy here, I'll put a white fellow for representing the hydrogen on it. Okay. So the blue guy has got two hanging and a white. Yeah. So this is going to be the carbon where the OH is attached. This is the oxygen. Oxygen has got two lone pairs, as you can see. These two which are hanging as it is are lone pairs. This white fellow is your hydrogen. This guy is the one which will do the hydrogen bonding. Yes?
Yes, sir.
Okay. Now, this is my fluorine. I'm going to connect the fluorine directly onto the neighboring carbon. I'm going to connect this fluorine directly onto the neighboring carbon here. All right, so this is how the flow looks now. So now, this is my eclipse conformation, correct?
Yes.
In this eclipse here, if I rotate it like this, what you're basically saying is I'm having a good interaction where these guys are as close as possible.
Yeah.
Right?
Yeah.
This is the argument here.
Yep.
Yes or no?
Yes.
Well, now what is the problem which happens over here? You're having repulsion between these two guys. You're having these repulsions. And most critically, you're also going to be having these guys are also going to be repelling each other. All of them are going to be repelling. Remember, lone pairs are not going to be occupying small amount of space. They are going to occupy a tremendously large amount of space. Because lone pairs are like fat fellows, correct?
Yeah.
Because you're only attracted on one direction, not on both directions. So now let's rotate this guy slightly into a gouge conformation. In this gouge conformation, as you can see here, this is a gouge where I'm going to be having, this is the fluorine here, as you can see. The fluorine is in a type of, what to say, inverted Y, and the back fellow is in a Y over here.
Yeah.
Correct? So the front is going to be inverted Y for you, and the back is in a Y conformation. This is a gouge conformation. So now in this gouge conformation here, have a look. If I rotate things suitably, I can get my hydrogen and guy into a direction where they are now nicely close enough, which is similar to the distance between the hydrogen and the lone pair in the previous case.
In fully eclipsed. Yeah.
Right? It is not as perfect, but it is very close enough. But remember, flexibility is allowed everywhere in this game here. When I say flexibility, you remember the ClF3 case in chemical bonding?
ClF3.
Chemical bonding, I would have discussed only very few structures, correct?
Yeah.
But I would have touched ClF3 for sure. I would have discussed the three different possibilities over there. I would have discussed basically talking about how the angles are different in each of those cases.
Okay, yeah.
I would have used an analogy using the pain centers with respect to the angle there. That applies here as well. The game goes like this. When you're going to be having something like this, you want to minimize the distance between them. But what is the true goal of hydrogen bonding at the end of the day? Go back to the true goal of what hydrogen bonding does. It increases stability of the molecule.
Yes.
So if I am going to be bringing in a hydrogen bonding, the purpose of bringing the hydrogen bonding in is to increase the stability.
Yeah.
Correct? So when I'm going to be doing this intramolecular hydrogen bonding, the ideal circumstance would be the best hydrogen bond possible is not the one which is going to be the one which is going to be closest for me, but it is actually the one which is going to be increasing my system stability to the greatest extent.
Okay. Makes sense. Okay.
So now you will have to start considering the hydrogen bond from, okay, this guy requires this parameter, but at the cost of not screwing the other systems beyond a point. In the eclipsed conformation, what is happening over there is, yes, you are having distance between the hydrogen and the lone pair of the system being as close as possible. But it is coming at a cost. The cost is you are making sure that every other bond is eclipsing the other. Which means increasing all of the other repulsions at the same time.
Oh, okay. Understood. Even though hydrogen bond is stronger, the others will.
Correct. That is what you are doing is you are making sure that the hydrogen bond is at the closest distance possible. Yes.
Yeah.
But it is coming at a cost at the other cases there. Because all of the other guys are also now having slightly greater increased repulsions.
Yeah, correct.
So it's like, yes, the boil on your ass is now most comfortably situated. But the rest of your ass is sitting on slightly thorny regions.
Yeah.
Understand the idea here?
Yes, sir. Yeah.
But the problem here is this. When you go into the gouge there, it is not obviously clear that the distance between the hydrogen and the lone pair are actually very similar still.
Yeah, that's what I was thinking.
That's why I wanted to show that to you. You could see they are very close by actually.
Yes.
So when you tilt them in right angle, they become very close by. Would you like to have a look at that again?
They're not. There's no guarantee that the lone pair is that
Did
close.
I finish my discussion here? Stop. What was the other point I talked about there? CLF3. What was the lesson in CLF3? You fucked up in CLF3 your exam. What was the fuck up you did?
So the angle, like, which is bond angle.
Good. What is happening? In real life, mathematically, whatever you decide is not going to be followed. It will bend and it will do shit. In this case, that's what it will do as well.
Okay.
See, it's like this. One guy has to bend slightly away to increase the interaction between the hydrogen there. That's all right. One lone pair has to bend. A lone pair is already only connected on one ending to the nucleus. It is very bendy. That is why it occupies a lot of space, correct?
Yes.
In the first place, the lone pair is something which is a very large group. It occupies a lot of space, mainly because it is only attracted on one end to a nucleus. The other end, it is free. If it's a bond pair, what's the system? The bond pair is having one nucleus on each end. Right? That's what a bond pair is. So that's the reason why the bond pair is something which is going to be attracted on both ends, so it occupies lesser space. The lone pair is already only attracted on one ending.
Yes. Right? Yeah, it has flexibility to move around.
Exactly. So the lone pair will bend now quite comfortably. It's not a problem about it at all to bend. So the one lone pair bending is far better than every other bond pair and lone pair adjusting, right? In that eclipse below.
Yes. Yeah.
So that adjustment will happen here far more comfortably. You have to make room for tiny adjustments being possible in the final structure. Because just like how when you have a boil on your ass, you will adjust and wiggle your ass as much as you can to adjust that pillow properly. Molecule will also do the same. Excepting in this case, the boil is not really a boil. It's a position where it gets more comfortable, that's all.
Yes.
A pain center or a comfort center are both the same.
Yeah.
At the end of the day.
Yeah.
Right? Energy-wise speaking.
Yes, sir.
They're a bump in the energy. Either it's a bump up or a bump down. Yes or no?
Yes, sir. Yeah.
Now, okay, all right. So let's come back to this here. So I'm assuming this is properly clear now,
Yes, sir. Yeah.
and
Clear.
you'll not come back to this again.
No.
So whenever you are going to be having hydrogen bonding, intramolecular being possible between two neighboring carbons, you're going to be having the gauge conformation being the best possible one. Why? Because it is not just that the hydrogen bonding is as good as possible. Yes, the hydrogen bonding can be better, but the adjustments required to be much more in another structure.
So yeah. Yes.
In this structure, the adjustments required to have the best possible hydrogen bonding are very minimal, and the rest of the molecule is in its more
Happy state. Yeah.
correct. Happy state is not a bad way of looking at it. Correct.
Yeah. Yes.
That's the
Yeah.
basic way to look at things. Okay. So I'm going to assume this is properly settled now then. Yes.
Yes, sir. Yeah.
So your conformer stability, I'll cross this shit off.
Yes, sir. Yeah.
Was this the only problem you saw in your conformer stability issue there?
So far, that's it.
So far, nothing else. Okay. All right. Cool. You have become very, I think chemistry has basically taught you how to converse now more carefully. You're starting to use more measured language. Okay. All right. Huh? Next was your cyclohexane. No? Cyclohexane, we had just started discussing the idea here. So let's fill in the blanks here. What is a structure if it's completely planar? All of them are the same conformation. Either it is y, or it is going to be
lambda. Sorry, inverted.
inverted y.
Yeah.
This is planar. Half chair is going to be something which is going to be a little bit of an awkward type of scenario. In a half chair, the structure will look like this. So in this here, you're going to be having so carbon 1, 2, 3, 4, 5, and 6. So 2, 3, 4, 5, 6 will be in one configuration, one will be in different. So in a half pair, you can think of it as y, inverted, 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 or it can be inverted y, 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 y. Half chair is also going to be, actually no, these three will be in same configuration. It's a weird one. This part will be in staggered, these three will be in eclipsed. That's the way to go about it. So you're going to be having not necessarily exactly this. It could be this, it could be different also. I think this is also fine. 1, 2, 3, 1 inverted now. This will be y inverted now, y inverted y. Correct now. This is staggered only. This is eclipse. Between these two, it doesn't have to be staggered or eclipse. So there will be 4 configurations possible actually for half chair. So 2 up and 2 down.
Yeah.
So chair is going to be your the one which we just talked about here. This guy is your chair, perfectly staggered. Whereas your boat is going to be partially staggered. I'm assuming these two are reasonably clear now so far.
Yes, sir.
Okay. Now, let's start talking cistrons now. Cyclohexane, what part did you not understand? I'm assuming you had clarity up to the different conformations and their stability.
Yes, sir. Yeah.